Okay, so analyzing puzzles and games. Let's start with the first game. It's very similar to Blinko in The Price is Right. And, uh, and so basically we have a little pebble and it's dropped. And it can land in A, B, C, D, E, F, or G at the end. And so how many ways are there to get to each black dot? So let's start with the first one. The first black dot, there's only one way to get there. How about this black dot on the left? It would only be one way. You can only go straight down, and the one on the right only one way as well. How about the very far other black dot right here? Again, one. You could only go straight down. You can't go back up because of gravity. And the other far right is one. So what about this guy? The one in the middle on the second row or third row? Well, let's move that arrow over out of the way. Okay. So this guy, he can come, we could either go, I'm just going to draw a little, like this, or like this. So there's going to be two ways to get to him. So let's follow this pattern. How many ways are there going to get, we're going to get to A? How many ways to A? So you'll notice, it should be one. There's only one way to get to A. It's either straight down this way. What about G? Should also be one. Only one way to get to G, straight down. Now we didn't finish this other black dot. How many ways are there going to get to that one? And that would be 3, because we could either come like that, 1, or we can go 2, 3. So you see that. I'll do it one more time. So 1, 2, 3. Okay? I'm just going to remove those. It's not so full. And you'll notice there's a correlation. If there's 1 to get to here and 2 to get to that dot, then there's obviously 3 to get, 2 from 1, 1 from the other way, gives us a total of 3. So this dot should also be right here, 3, because we have 2 and 1. It's very similar to something called Pascal's triangle. So here, how many ways to get there? Well, if there's 1 from the left and 3 from the right, it'd be 4 total ways. How about that dot? Well, 3 and 3 is going to give you 6. 3 from the left, 3 from the right. How about this dot? 3 from the left, 1 from the right is 4. And so the pattern continues. So this guy would be 5. Here would be 10. Here would be 11, or sorry, 10. And then 5, 4, and 1. And so to get to B, there's 6 ways. To get to C, there's 15. D would be 20. E would be 15. And 6 ways to get to F. So that's a really cool pattern. It's a special pattern. It's called Pascal's triangle. And so did we use inductive or deductive reasoning? And the answer is inductive. Why? Because we used a pattern and then we repeated that pattern, right? Each number above, we added it together. It's so whenever we take a pattern and we draw a conclusion, that's inductive reasoning. Remember, also inductive reasoning, we often use numbers. We're working with numbers here instead of letters. Okay. So use your strategy in, oh, so we already did that. Okay, so let's move on to the next page. I'm just going to note that this is very similar to Pascal's triangle. We've seen this in previous questions. Pascal's triangle. Okay. So here's a problem. I'm going to go on to investigating inductive and deductive reasoning in game and puzzles. And so I believe this is pronounced Wen, or Win, and Henry play the simplest variation of NIM. And so what NIM is I'm just going to read this part here. Players may remove as many objects as they wish, so as long as objects come from the same pile on that turn. The game can be played in 2 ways. One is either the player with the last object loses, or the player who takes the last object wins. So Win and Henry play the simplest variation of NIM, so to see if a winning strategy can be discovered. They set up 1 pile of pennies, and each player must remove 1 or 2 pennies, only from the pile, alternating turns. The player to remove the last penny is the winner. So Wen will be player 1 and Henry is player 2. And so they begin. And so basically they start with 1 penny. Move this up here. And so if player 1 gets first turn, they get to take it, they automatically win. And so that whenever there's 1, player 1, so if they take the 1, they're going to win. Now if there's 2 pennies to start off with, there's 2 pennies, player 1 will still win because they are allowed to take 1 or 2. So they take both, 1, 2 away, then they have won. So they've already started this table onto the right, as you can see. So if you play the game with 4 coins, can you come up with a strategy for player 1 to win? So down below, actually let's bring up some more coins. Or I could just even use on the down here. So we have 4 coins I have right here. I made them 4 sticks or ovals right here. 1, 2, 3, 4. So if I'm player 1, I want to win. So let's say I picked number 1 stick. Now I have 3 left over. So player 2 is allowed to take 1 or 2. If they take 1, then I can take both 2 away and I win. So that's okay. So that's if I picked 1 to start with. Now if I took 1 to start with and they took 2, I would still win. So notice when there's 4 turns, I really want to take 1 to start off. What if I took 2? Well, if I took 2 to start, because I'm allowed to take 1 or 2, then player 2 could win by taking both. So that's not good. I really want to take 2, go back. I just undo that, whatever I did. I really want to make sure I take 2 to start with, or 1 to start with, not 2. Because if I took 2, then they could take 2, and then they would win. So really the key here is player 1, I want to take 1, because no matter if they take 1 or 2, then I win. So on the very next page, there's a table started. So already with 4, the key is I had to take 1, and then I would win. So what about 5? I'm just going to go back. What about 5? So what if instead there was 5 different pennies? 5 different pennies. Let's move one of these over there. Okay, so there's a starting pile. I'm player 1. Player 1, if I take 1, then there's 4 left over. Okay, so now player 1, let's say they take 1. Now I could take 1 or 2. Now I'm in trouble, because if I take 2, they win, or if I take 1, they also win, because they can take 1 or 2. So taking 1 wasn't a very good strategy. Let's try it if I take 1 and then they take 2. Well, they probably wouldn't do that, because then I would win, so they would have taken 1. So me taking 1 wasn't very smart when there's 5 on the table. If I'm first to go, I want to take 2. Oops. Now I should be in a good place. They take 1, I take 2. They take 2, I can take 1, so I would win. So it's very important, if I'm first to go with 5, I want to take 2, and then I'm going to win. What about 6? So let's try now with 6. Let's put these all back in here. We have 6, 4, 5, 6 pennies. So I'm player 1. So see, we want to see if there's a pattern. If I take 1, there's 5 left over. Now, if player 2 is smart, he'd actually take 2 and leave a multiple of 3. So this is where strategy comes in. Now, if I take 1 or if I take 2, he should win, because he's allowed to take 1 or 2. So what if I start off with taking 2? So right now player 2 won. So what if I took 2? If I take 2, player 2 can win again if he only takes 1, because now he's left 3. Now I'm forced to take 1 or 2. No matter what, I would win. So if there's 6 tiles to start off with, I'm kind of hooped. I could take 1 or 2 and player 2 will win. Do you see a pattern here? You should see a pattern. So what the next thing should be is that with 7 pennies, I should take 1 and I should win. So let's try that out. So the key here is always going to leave a multiple of 3 for your opponent, and then you're going to be in good shape. So there's 1, 2, 3, 4, 5, 6. We'll add one more. Oops. There Add one more. So I have 7 here. It told me that I should take 1. So I take 1. Now there's 6 left over. Now say my player 2 takes 1. My strategy should be to take 2. Remember, we want to leave them with 3 so that whatever they take, 1 or 2, I can take the last ones or last one and I win. So again, what we have to take 2 to begin with, right? You want, or 1 to begin with, no matter what. So let's try it again. So it's saying, oops, if I am player 1 and there's 7 different pennies out, I want to take 1. So I take 1. Now let's say player 2 takes 2. Then again, I want to be able to leave 3. So I should be doing opposite of the other player to always leave that multiple of 3. Then if he takes 1, I can take 2. If he takes 2, I could have taken 1 and I win. Okay, so that worked. So, did I lose a page? I think I deleted 2 over. There you go. So that pattern does follow. So if there's 8, again, I should take 2 to start off with to make 6, and that would win. If there's 9, then I should lose. I could take 1 or 2, and player 2 plays it right. He should always win. If there's 10, then I should take 1. It's that pattern, and I should win. So just really quickly, going back to this page here. So wait, now we have 1, 2, I could go, say there was 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if there's 10, or we can do 11. Let's do 11 pennies. Okay? As player 1, I know I should win. All I have to do is always make sure there's a multiple of 3 for the other player. So there's 11 here. That means I want to take 2 because I want to leave 9, which is a multiple of 3. Now my strategy is just to do opposite of what the other guy does. So say he takes 1, then I want to take 2 because that would still leave a multiple of 3. Now there's 6 left over. If he takes 2, then I'm going to take 1 because now there's a multiple of 3 left over. We want him to leave with 3 because now he could take 1 or 2. Either way, I win. I take both. Okay? And so there's that strategy there, because we always want to leave the other player with the multiple of 3. With the multiple of 3. So let's answer the following questions. What is the smallest number of coins that can be left by Henry so that Henry knows he'll win? And that was 3. Well, no, it's the smallest enough. Remember, Henry was player 2. So Henry knew he would win if there was 3. It's Wynn's turn. What is the second smallest number of coins that can be left by Henry so that Henry knows he'd win? And that was 6. So second player would always win if there's 3 or 6 or 9. Wynn and Henry realized that a winning strategy may involve a link between the number of pennies in the pile and the number of pennies the first person removes. Play the game several times with 7 pennies and devise a strategy so that player 1 wins. So player 1 should always grab 1. Leaving 6 for player 2. Right? We always want to make a multiple of 1. Player 2. Then player 1 grabs the opposite of player 2. So player 2 grabs 2, he grabs 1. Player 2 grabs 1, he grabs 2 of player 2. And then he should win. Okay, so then you're going to leave with 6, and then he's set down to 3. So repeat phrase. So we finished that. And now let's answer the last part. Which player, first or second, has control of the outcome of the game if the original number is, let's start with 12. So 12 is a multiple of 3. That means player 2 would have that control. How about 25? Is 25 a multiple of 3? So if you're not sure, you can go 25 divided by 3. And no, it's not. So player 1 has control. In fact, how many sticks should he take? He wins. Well, We want to make it a multiple of 3. 24 is the next, oops, 24 is the next multiple of 3, grabbing the calculator. So 24 divided by 3. So he would want to take 1, so that it makes, so he should take 1. 50, is 50 a multiple of 3? If you're not sure, we go 50 divided by 3. No, it's not, so player 1 has control. How many should he take? Well, we check. Okay, does 49 to go into 3? 3 to go into 49? No, so it must be 48. He must take 2. So he has to take 2, and then he'll win. He could win. Take 2 on the first draw. 300, so 300 divided by 3 is 100. So that would be player 2 has control. All right. Moving on to the next page. Brianne and Joanne choose any 4 days in the month of September to form a square as the example is shown. Brianne told Joanne to tell her only the sum of the 4 numbers. So she makes a square and add them up. And with that, she could predict what the numbers were. So Joanne said, okay, the 4 numbers add to 72. So Brianne said, oh, well then your numbers have to be 14, 15, 21, and 22. So let's double check that. 14 plus 15 plus 21 plus 22. And sure enough, she was correct. So Brianne used deductive reasoning to determine the numbers. Remember, deductive is where to use letters. We want to do a proof. So part of her reasoning is completed, and we're going to complete the rest. She said, let n be the smallest number. So if n is our smallest number, what's the 14, for example? How are 14 and 15 related? If n is your smallest, then 15, or your next one, would be 1 more than that always. 5, 6, 1, 2. And so the next smallest numbers are n plus 1. How about this 21? What's the relationship between 14 and 21? Or 5 and 12? Or 7 and 14? Or 9 and 16? 10 and 17? You should notice that it's 7 more. It's a week later. So n plus 7. And last one, 14 and 28, be n plus 8. It's 1 more than the week. And n plus 8. So what are we doing with those? Well, we know the sum is going to equal to the n plus the n plus 1 plus the n plus 7. Put them in brackets if you like. Plus the n plus 8. Okay, so let's devise, okay, how does she figure out what the smallest number is if she knows the sum? So let's collect like terms. We have 4n, and 1 plus 7 plus 8 is 16. So what does she do? If we want to figure out the smallest number, our n is our unknown, how do we rearrange this for n? We can subtract 16 to both sides. So our sum minus 16 equals 4n, and then we divide by 4. And so our smallest side is our sum minus 16 divided by 4. That's how she can come to her answer. So with your calculator, your sum was 72 minus 16, and then divide by 4. 14 was the smallest day. And that's the end of this part of the lesson.